Greetings, welcome back to my channel. This is the next video in my series on the Racket programming language, and we're going to look at some basics for manipulating strings. And as a motivating example, we're going to look at creating a program that matches simple regular expressions. Regular expressions that in this case basically look like the following. Where you can either match a single character or any character, that's what the dot means, any character, or given the star after that means zero of whatever's before it. So this part here is zero or many whatever characters, and this part here is zero or many C characters. So to do this, we're going to borrow some of the basic ideas from what's called Elixir in computer science. Elixir is just a thing that takes a large text file and turns it into a series of tokens as fast as possible. The first version of Elixir was called Lex. It was a program that was available in a lot of environments since the 1970s. The GNU Linux version of it was called Flex, and is basically has a few more features, but still harkens back to the basic syntax of what Lex used all the way back in the 70s. And you can do some more research on that. We'll go into the syntax of that down the road. But for now, we're just going to take the idea that we want to turn that string, that regular expression, into a set of tokens. And so that's the first part of what we've done here. So this is our tokenizer for a regular expression. We handed in a regular expression string here. First of all, if we've processed all the string, we're just going to go ahead and return an empty list. Our goal of this tokenizer is to return a list of tokens. And otherwise, we're going to do the following. We're just going to let the first character equal string ref. And what string ref means is take the, given this index starting at 0, return that character in the string. So this is the first character in the string. So, okay, on the case, now we're using a new form here, a special form in Racket called case. So we're going to switch on the first character. If it's a backslash, what we're going to do here is the following. If it's a backslash, we're going to assume that this is an escape sequence. So if we wanted to match a dot here, we could use slash dot to match a dot. So what I'm doing here is that if the string is only one, has only had one character in it, then this slash doesn't make any sense because we have to have something following that slash. So that's why that error is here. Otherwise, we're just going to, boom, stick in that character, we're going to stick in that character into the list, and we're going to tokenize the rest of the string. So we start at 2 because we're taking two characters here. We're eating the slash, so to speak, and we're eating the character after it. If we have a dot, I'm going to cons a dot token and do this kind of thing here. And same for the star, I'm going to do a star token. Otherwise, I'm just going to cons up the character and cons that with the rest of the list. So recursively going through that string. Now, I could add this char token here to basically each one of these characters. But what I realized is that this would actually make things a little bit more difficult in the programming. And one of the great things about Racket being, dynamically typed is I can just go ahead and check to see that if I have a character, the way I can determine that is if the first thing in this rule or the first thing in the token list is indeed a character. Now, the second thing I'm going to do is I'm going to now, given this tokenization, I'm going to actually parse it and create a set of rules from this token list. And a rule is a list like as the following, which, I say here in the comments, very simply, in this case, this is a rule that says, here's the character A, match it one time and one time only. So this is the minimum values that you can match. This is the maximum value. And you can see that a 0 minus 1 is what we use to represent a star. So that's what we do here is we go on, do things over this list, the token list now. Obviously, since we're going over a list, we do the standard type of thing where if it is empty, we return the empty list. If the length of the token list is 1 here, so we have the last token to parse, Well, if the last token is a star, then something's wrong. That star didn't match up with something before. There wasn't a character before it. And the reason being is that if you look at what we do here, we eat up we eat up a star and its preceding token. So otherwise, we go on ahead and create the new rule, which is basically match that character one time and one time only. Otherwise, I'm going to set up two things here. Since I know that the length of the token list is actually now greater than 1, I can go ahead and say, here's the current token that we're looking at, and here's the one that's next to it. And the reason I'm doing this is I'm looking ahead for stars. First of all, like as if I had seen a star here, that's going to be a problem because I shouldn't be seeing a star. And so I'm just going to return an error here. However, if I see the next token is a star, then I know that I have this. I want to make a rule that says, okay, match 0 or many of the current token, and then go off. And note here I'm doing the CDDR token list, which is basically not just taking the rest of the list after the first item's off, but taking the rest of the list after 2 items are taken off. And the default case is that, well, we're just going to this is going to be the current token, and it's going to match at minimum 1 or many times. And then we're going to const it up with recursive call to the regex match list. Okay. So now we've created these rules, and this is a very simple way of parsing. And if you look at this, if you look at a regex, we're very lucky that this simple red example, we can see exactly what to expect by just looking at one token ahead. In more advanced parsing cases, you actually have to look a certain many tokens ahead, or go through a more complex process in which you try to define or parse a grammar by moving one token ahead, and that determines which rules get called at the next point. We will discuss that kind of parsing later on. So the next thing we're going to do here is that I'm going to actually do kind of an optimization. And so this is what this collapse match list does. Is again, it's going to go over this list and it's going to try to make more optimized rules out of it. And what that does is, if you think about it, if we have something like in a regular expression, well, that's the same thing as this, right? And if we have something like this, then we want to try to turn that into something that looks like a rule like 2 or more A's, right? So that's what this does. Again, we go off, and if it's empty, we just return the empty list. If the length of the match list is 1, we just go ahead and return what the list is, because there's nothing more we can optimize. There's nothing after that we can do. Now, again, as we did before, we look ahead. We take the current match rule, and we looked at the match rule after it. Basically, and we do the following. If the 2 rules don't match the same character or match any character, then we're not going to be able to collapse them. So then, if that's not the case, we're just not equal, we're just going to take that current rule and match it to whatever the recursive call to the collapse helper is here. Okay. Otherwise, I'm going to make a rule that combines the 2 rules together, and it uses this kind of formula that I talk about in the list here. And basically what that does is it kind of does the math to sum up, basically if you sum up the amounts of minimums and maximums. So it goes off and it says, okay, take the character there, for the minimums, just add the minimum for the current match to the minimum for the next rule. For the maximum, it's more tricky. What you need to do is we need to check, so if either rule is or many or more, then we just keep it as that. Otherwise, we add in, like we did for the minimum amounts we match, we do the maximum things we match. All right. And now we go off and we just recursively call this, having swallowed that rule up. Now here's the interesting part. We have this helper here. What we do is I'm just going to let the collapse list start out with the first call to this collapse header for match list. And then if that collapse list is equal to the match list, the length of the match list that we're passing in, then just return the class list. We don't have any more work to do. Otherwise, go do another pass through that collapse list and see if we can collapse things down further. Now, what this does is that this does mean that we're kind of going through this list multiple times, and we're not trying to optimize everything at once. However, it does simplify the logic here to the point where that makes more sense to do multiple passes versus trying to do every single possible thing in one pass. It gets more complicated and it'd be harder to read. And since you're already doing this once for a regular expression, it kind of makes sense. So what I'm going to do is I'm going to go ahead and scan a regex and see what that returns here. And we're going to go A, B, A, star in this case. And let's see what it returns. And over here, we can see we have the following rules. It has collapsed this, saying we have to match the character A minimum and maximum of 2 times. We have to match the character B once. And then we have to match the character 1 or more times. So that's gone and it has worked. Now the thing about that is that given this, you can see that this is kind of the essential thing that we're going to go over and try to do by matching these rules and using that to consume a string. And if we can basically consume an entire string and exhaust all the rules, we know that that string has matched that regular expression. And that's what we're going to discuss in the next series. So the basic things that we learned from terms of messing with strings or processing strings is we've learned the string ref thing, which takes the nth character here, where n is this integer, and we also have introduced the substring, where substring in this case has the form that just starting here, take the rest of the string. There is also a substring version of the call that takes 2 numbers, which basically says, oh, okay, start here and then go to the next, that index. So that can allow you to take a substring like from 1 to 5 characters or 1 to 7 characters, so on and so forth. If for whatever, in this case, we don't need to really do that. So we just use these 2 types of things. Okay, so that should give you a little bit more ideas on how to do some basic stuff with strings. As note that, again, the definition of a string and operating over a string is slightly different than what we do for lists, but it still has kind of the same pattern. If we have an empty string, return whatever, and otherwise do something with the first character, and then go ahead and take that and tokenize it. Now, since we're turning a string into a list here, we're using lists. One of the things you might want to do is, as a programming example, go ahead and define something like and what that would do is take every character in the string and turn it into an uppercase version of that. Basically, every character would now become an uppercase version of that character if it wasn't uppercase already. So just turns the entire string into uppercase. And that would give you an excellent way of understanding how to do the basic manipulation with strings. So some of you more advanced programmers might have noted that one of the things that we haven't done here is that we have not done anything in terms of mutation. I've not set a value to update to another type of value. And the question might come up is like, is that even possible in Scheme? And the answer is yes. We will eventually get to some examples where we do this. But it's kind of interesting to know how these recursive definitions and also these lets kind of allow us to do this in a way that we don't have to basically mutate a lot of state, but rather track it through recursion. And the thing about that is for advanced people that look at this and say, well, this might look inefficient. The reason it's not as inefficient as you might think is that modern processors have made function calls very fast. Not only that, but allocating things on the stack, which is what we are doing here, in such a manner that they're not mutable, actually is very fast. Now, there is, in terms of space overhead, that means there's sometimes space overhead. And certainly it's why you need garbage collection, and that's why Racket is garbage collected, is that it really makes sure that stuff doesn't live on. But a lot of this can be optimized to use not very much heap memory versus stack memory. And again, since stack allocation is so quick, that really does lead to a fast program. To give you an idea, when I discuss the next part of this program here on how we can actually take this list and then match it, I can show you what I did in LeetCode and the runtimes, and that it was actually surprisingly performant. And while using not an insignificant amount of memory, was not actually as bad as I thought in terms of memory usage. And I was certainly surprised at how well it worked in terms of overall runtime. Anyway, that's my latest video. Thanks for watching, and I'll see you in the next video.